Hi everyone, welcome back to my channel after so long. Today we have a beautiful problem here from the International Math Olympiad 2021, which just happened like a week ago. So the IMO, where's my pen? Let me choose color. Okay, why is it not writing? Okay, the IMO 2021. And at first sight, this problem might seem a little hard because there's like these 8 lengths that we have to show that the sum of 4 of them is equal to the sum of the other 4, and that kind of might be intimidating for beginners. But you should keep in mind that this is like an IMO P4, and IMO P1s and 4s usually don't require any like complex stuff. There's usually they can be solved using basic elementary stuff such as angle chasing and power of the point, and maybe some clever construction at times, but it's just about making use of the things that are given to you. So just make a list of like the givens that are in the problem, and then one by one try and interpret them in some way. So I encourage you to pause the video and try the problem out on your own, and obviously draw your own diagram on paper with like a pencil and compass. So assuming you give it a shot, I'm now going to show my diagram here. Okay, so this is the diagram. So we have a circle here. This is the small circle, and basically we have a tangential quadrilateral here. So the 4 sides of this quadrilateral are all tangent to this circle here. And then in the center of the circle is I here. So this is the circle, and we have our tangential quadrilateral, which is ABCD. And then we have another circle, which is actually the circumcircle of AIC, where A and C are 2 of the points which are opposite each other in the tangential quadrilateral, and I is the center of that quadrilateral, the circle, the incircle of that quadrilateral. And they're saying the BA, the line BA, if you extend that, it meets the circle omega at X. And similarly, we have the extension of BC beyond C, it meets at C. And then we have the extensions of AD and CD, which meet omega at Y and D respectively. So AD meets it at Y, and CD meets the circle at D. And we want to show somehow that all of these lengths are equal. And now I think there's a number of ways to finish this problem, but I'm going to show you the one that I find the most elegant and simple. And I think there's one thing that's true in all the solutions here. And I encourage you to really look at the diagram, maybe this diagram or yours, and try to figure out that one claim. Use the things that are given to you and try and figure out some claim, something that's true in the diagram. There's always things you can find by looking at your diagram. Things that maybe some points look collinear, maybe some points look concyclic, that they're in a circle, maybe some lengths are equal, maybe some angles are equal. So try and pause the video and figure out something that could be true based on the facts that are given. So figure out a claim and try to prove that one claim, which is going to be really crucial for our proof here. I'm going to erase this on the side and let you figure that out. Why is it not erasing? Actually, I'm going to show you a different result here that might help you reach that claim. So let me just erase this stuff right here, and let me scroll down and show you a separate result. So let's say you have any circle. So let's call this the lemma or the result. It's actually pretty obvious, but if you're someone who's not seen this before, let's see. So we have any triangle ABC and its circumcircle, and we make the external angle bisector of any angle. So in this case, let's say BAC. So we choose this angle from this triangle, and we make the external angle bisector. So it's defined, this line, it's defined as the external angle bisector. So if you extend the line AC, there's a line such that this angle, let me go to this layer. Okay, so this angle right here, if this is alpha, then this angle is also alpha. So this is just the way this line is defined. So our claim is that the external angle bisector of BAC, it meets the circumcircle at the midpoint of the arc. Which arc? It's just going to be the arc that makes that angle in the first place, like the chord that makes that angle. So BC subtends this angle BAC, right? So the midpoint of the arc BC, which is in the same side as A, that's the point where this angle bisector is going to cut this circle. So that's what we're saying. So how do we prove this? Actually, try and pause the video and see if you can figure it out. It's a very basic angle chase. So basically, if I make two lines here, let me make this line MB. We know that because this angle E is just any point on the AC extended. So we know that EAM, so angle EAM is equal to alpha, but we know that this is the angle which is the exterior angle opposite to angle MBC. So they have to be the same. So angle MBC, because this is a cyclic quadrilateral, MBCA, angle alpha has to be equal to angle MBC, because angle MAC is 180 minus alpha. So angle MBC has to be alpha again. But notice if I also make the line MC here, then angle MCB is also equal to alpha. Why? Because angle MCB is equal to angle MAB by the angle in the same segment are equal theorem. So because they're subtended by the same chord in the same circle, these angles are equal. So now I'm going to make these angles. So this is alpha and this is alpha. But this means that triangle MBC is isosceles, and basically MB is equal to MC. So we are done. So we now know that M is the midpoint of the arc BC, because MB is equal to BC. That's what the definition of the midpoint of an arc is, because it's on the perpendicular bisector of BC. So now try and use this result in our problem above. So maybe now pause the video and try to figure this out. I'm going to scroll back up here. Hopefully this made sense. Now try and spot the same result here and reach some claim. Assuming you've given it a go, I'm now going to show it to you. It's pretty obvious. We can see that right here, if you focus on, let me actually make the lines XY maybe, and DZ. So now focus on this quadrilateral, this triangle, basically XAY. So if you notice that the line AI, so I'm going to write down the proof now for the problem. So AI is the external angle bisector of angle XAY. So what does this mean? This means that essentially because the external angle bisector meets the circle at the point I, we know that I is the midpoint of arc BC. Sorry, the midpoint of XY. Similarly, we can say that for the triangle ATZ, if you focus on that, once again, AI is the angle bisector, the external angle bisector. Oh, actually no, we're not going to have to focus on CI. So focus on the triangle CTZ. So I'm going to write here for triangle AXY, and now let's look at triangle CTZ. So because CI is the external angle bisector, we now know that I is also midpoint of TZ. But this is really nice. Why? Because this automatically implies something that's going to be very helpful. Because TZ and XY have the same arc, same midpoint of their arc in the circle, this means essentially they're both parallel. So all of this implies that XY is parallel to TZ. It's not really clear. You can obviously look at it this way, because the perpendicular bisectors of both these lines are going to be the same, because that's how the midpoint of the arc is defined. It's the point where the perpendicular bisector of any chord intersects the circle. That's the midpoint of the arc. So because I is the midpoint of both of these, the arcs made by both of these chords, we know that they have to be parallel, and this automatically implies that essentially xt is dx is equal to yz, and this is huge. Why is this true? Because obviously if you have a parallel line inside it, if you have two chords that are parallel, they obviously are going to make an isosceles trapezoid, because the only trapezoids that are cyclic are isosceles trapezoids. So essentially xt is equal to yz, and this will simplify our problem statement, because now we can just cross out the dx and the yz, because they are both equal to each other. And at this point we're almost done. There's a number of ways to finish here, but I'll give you the hint, which is equal tangents. So just using equal tangents at this point, it's possible to finish this off. So I encourage you to pause the video and try and figure that out. I'm gonna maybe erase this part here and then show you the final part, or maybe I can just scroll down. Yes, let me scroll down and try to complete the proof. Okay, so let me choose a different color. So this is the first part. Now we need to show that AD plus DT plus XA is equal to CD plus DY plus ZC. So now we're down to three lengths. We need to show that the sum of these three lengths is equal to the sum of the other three. So try and find these lengths in the diagram, and then maybe convert them into something. So the hint at this point would be to try and convert these three lengths into the sum of three lengths into the sum of two lengths using tangents. So maybe pause the video, try it out. The way to do it would be, for example, we have AD here. So you can see in the diagram, just for fun, I made these four other points that were not given. These are the points of tangencies of this in circle with this quadrilateral. So there are 4 points: E, F, G, and H. So I can write AD as AH plus DH. So that's what I'm going to do. I'm going to show it to you for one side, and the other one should hopefully be obvious. So I'm going to write here. So AD, I'm just going to write the whole sum one by one. So for AD, that's going to be AH plus HD. And then for dt, well, there's no way to rewrite this as tangents, right? It's pretty much the same, so let me just keep it that way. And then xa, so let's see, where is xa? So we have xa. There's also actually no way to rewrite that as well at this moment. So now, because of equal tangents, we know that AH, this length here, is equal to AE right here. So instead of AH, I can write AE, and that's what I'm going to do. And it'll be clear why we're doing this in a second. And instead of DH, I'm going to write DG. And the rest are just going to stay the same. But notice, the idea was to bring these lengths on a straight line. So now AE plus XA is just going to be XE. So I'm going to rewrite this. I'm going to join these two, and I'm going to make this XE. So this whole sum is now equal to XE plus, let's see, DG plus DT. So DG is this length here, and DT is this one. So because they're on a straight line, we can, and there are the points are, there's a common point, we can turn it into one length. So I can write this as DG. So now we want to show that this is equal to the sum of these three. But notice we can do the same thing for them as well. Let me do that in a different color. So for them, once again, I can write CD as, where is CD? So I can write that as, so I'm going to just put this in a box here, so you know this is for these ones, and for these ones I'm going to write here. So CD can be written as CG plus DG, and dy and zc are just going to stay the same. So dy plus zc. But once again, we can do the same trick. We can join them together. So we can say cg plus which one? So we can say that cg, wait, so we have cg and dg, and what do we have? We have yz, oh sorry, my bad, this is zc. So we have zc. So I can write cg as cf, because notice by equal tangents, the point C has two tangents here to a circle, and both of them have to be the same. So CG is equal to CF. So I can write, instead of CG, I can write CF. So this is probably a little messy, but hopefully I can finish it up on this page. So instead of CG, I'm going to write CF plus CZ. And then for the other two, so DG is equal to DH. But that plus dy is just going to be, so dy plus dh is now going to be yh, and what's the other one? So cf plus cz, that's going to be zf. So now the problem is down to showing that zf plus c plus yh is equal to xe plus dg. But believe it or not, we're done at this point. And why are we done? Because each of these lengths, all of these lengths are tangents to this small circle. So because they are tangents, and notice this xe is just the tangent from x to this circle. Right? There's only going to be two possible tangents from a point to a circle, and one of them is xe. And ZF, and sorry, YH is the tangent from Y to this circle. So the tangent of Y to the circle. But these two have to be equal, because essentially we know that IX is equal to IY, because I is the midpoint. So we know that IX is equal to IY. And similarly from here, T is equal to IZ, and I is the center of the circle. But this is very important. It does not make sense. I can maybe show you a small diagram here. think of this circle and think of this point, and I'm going to draw a tangent here. So essentially you can always use the Pythagorean theorem to essentially form a relation between this tangent and the radius and the distance of the point from the center of the circle. So because the distance of x and y from the center of the circle is the same, and obviously the radius is the same, so essentially the tangent for each of them, let's say one is x, so x is just going to be, let's say the distance is ix squared, because it's the hypotenuse, minus the radius squared, and the square root of that. This is just the Pythagorean theorem. But this has to be equal to, let's say the other tangent is y, but because iy is the same, essentially both of these lengths are the same. So that's why I can cross these out. I can say xe is equal to yh. And using the exact same logic, I can say that tg is equal to zf, because once again, t and z are equidistant from the center of the circle. So their tangents to the circle must be the same length. And that solves the problem. So thank you so much for making it to this point of the video. This is actually my first video on Olympiad problems, and I actually could not solve this problem during my own test, which is kind of sad. But I'm just going to hopefully keep making these videos. And please feel free to leave any feedback or suggestions, and have a great day.